So just like every other question, we start by factoring. The bottom is a difference of squares. Step 1, state our non-permissible values. X can't equal -3. X can't equal 3. Another common mistake that sometimes happens is after you factor, you might have noticed already that we have a factor that's exactly the same in our numerator and our denominator. So sometimes people get really excited about that, cancel that out, which it does cancel out, but then they forget to list the -3 as a non-permissible value. -3 is still a non-permissible value. Okay? Whenever something cancels out, you get to write your new equation. I would like you to write your new equation from canceling it out. Because again, here's a place where it's really easy to make a little mistake. And if you make that little mistake when you write the equation now, I want you to be aware of it so you don't make it on a test or a quiz when it's more important. Here's the mistake. I'll write the mistake in red. Y equals x minus 3. Here is the right way. I'll write it in green. Y equals 1 over x minus 3. Okay? X plus 3's cancel out. You're only left with the x minus 3, so you're very tempted just to write y equals x minus 3. But we have to remember that that x minus 3 was in our denominator to begin with. It needs to stay in our denominator. That means there's nothing left in our numerator. We have to write a 1. Technically, when things cancel out, some teachers would advocate, oh, you should never use the words cancel out. You should always say simplify, because it simplifies to 1 over 1. So that's why there's still a 1 there. I don't know, it seems fun to say cancels out. Feels more invigorating to cancel something out, right? There's a lot of pent-up math rage, so stroking those things out is really quite liberating. But you will get a 1 left on top. And I wrote it in green because now this is our new equation. We now graph that equation. And it's still a rational equation. Up till now, every time we've canceled something out, we've always got a boring old line. So we drew our boring old line and added a hole. Now we've got a rational function and it has a hole. Okay? The minus 3 canceled out. So that means we are going to have a hole at minus 3 comma something. And we are also going to have a vertical asymptote because the 3 didn't cancel out at x equals 3. What's the something? (1 over -6). Good. So now we know we have a hole and we know where it is, -3, 1 over -6. And we also have a vertical asymptote at x equals 3. Now when we go to step 2, because it's still a rational function, we now do our horizontal asymptotes and oblique asymptote based on our new graph, 1 over x minus 3. We don't look at our original graph now. We, from now on, look at the green equation for everything. Do I have a horizontal asymptote or an oblique asymptote? Well, the degree is larger in the denominator. Anytime the degree is larger in the denominator, you have a horizontal asymptote. And that horizontal asymptote, when the degree is larger in the denominator, is at y equals 0. Yes? This is a situation where it doesn't affect the results. But if we go back to example 1, okay, if you went to the original equation here, you would say oblique asymptote. Because the original equation has higher degree in my numerator than my denominator, which is normally an oblique asymptote. But because we had a hole that simplified this equation to just a line, there is no oblique asymptote. So having gone back to the original one would have told you something false. So that's why I'm trying to stress that if you get that new equation, that green equation, which I've always drawn in green, we graph that from there. In this case, it would have been the same for the horizontal asymptote. You would have got y equals 0 in either one. Okay, step 3, x-intercepts and y-intercepts. Here, it's very important that we go to our green equation. Because in our green equation, if you plug in 0 for x, okay, you're going to get 0, 1 over negative 3. And when you go to your x-intercepts for your green equation, and put y equal to 0, when is your numerator equal to 0? Your numerator is 1. When is 1 equal to 0? Never. There are no x-intercepts. Again, had you gone back to the original equation, for your y-intercept, you would have got 3 over negative 9, which simplifies to 1 over negative 3, which is fine. However, if you would have gone to your original equation for your x-intercept, you would have said there's an x-intercept at negative 3. In reality, there isn't. There is no x-intercepts in this graph. So again, it's very important that if you do have a hole and it simplifies, you now graph your new equation and add the hole to your new equation. You don't go back to the original after that. So if we start graphing this, and we put the information that we already know. We know we have a vertical asymptote at x equals 3. We know we have a horizontal asymptote at y equals 0. We know we have a hole, oops, at negative 3, negative 1/6. We know we have a y-intercept at negative 1/3. And we know that there are no x-intercepts. Our graph splits this into 2 sections. We have points in the left section. So we could finish graphing the left-hand side. But for the right-hand side, we need another point. So I'm going to go to my purple pen, go to my green equation, because now everything goes back to the green equation. Something to the right of x equals 3, I'm going to plug in 4. If I plug in 4, I'm going to get 1 over 1. So I know that I have the point 4, 1. And now that I have a point in this section, I can graph it towards the asymptotes. Oh. Take out a red star by question number 4, because on the past 4 years of the exam, this has been a favorite on the exam. They like graphs that have a hole but still have asymptotes. So here we still had a rational graph that you had to use all your rules, plus you had the rule of the hole to come in. Because if they just do the ones with a line, they're like, oh, we're really only testing if they know how to graph lines. But this way, they're testing, do they know how to graph the rational graph plus if it has a hole in it? So this has been the most typical one. And unfortunately, you know how I give you questions after every one that I give you? There is none in the textbook that are like this one, other than this one. So I'll give you some other practice in class with ones like this, but there's no additional homework tonight.